and back with us, and we're still working on his gravity stuff. And again, just another great friend. I just want to bring up Bobby Hilster.
Thank you for
Mike.
Thanks Greg and my son David for helping out get this thing organized, and especially thank you people for even being here Friday afternoon. 4 years ago I gave a presentation here in Albuquerque, not in this place. I was the last speaker on Friday. At that time, 10 people. The whole conference was only 30 people. So it was pretty small at that time. So I appreciate you being here. I'm going to be talking about the Wang Eclipse and actually also the anomalies, which are all considered anomalies in their own right. Qien Shen Wang with others measured a gravitational effect of a full eclipse on March. I'm not going to pay attention. On March 9th of 1997 in China. A gravimeter measures the vertical gravitational acceleration at the point where it is placed. Wang took the measurements, subtracted the average value, and plotted the difference. He also put points on the curve identifying the visual eclipse. And this is the curve. Yeah, there I go, I did that before. Oh, come on. One of these days I'll get this right. Okay, the bottom line is a timeline, and this zero line is apparently represents his average, and all these little dots are the actual readings after he subtracted out the average, and then he did a 10-point running average of those points, and he got that curve. Everybody looks at that curve and says, oh, that's not right, and they throw it out. It's an anomaly. But I couldn't let it go at that. I already just said that that particular one. But the attention goes to the bumps because they don't make sense. And but I decided to look at the bumps a little more closely. So I drew some lines on the chart, and on the lines, the paper he reported on actually stated the sun as 2 hours, 13 minutes, and 21 seconds. I divided that in half, and at the totality then gave a line here being the start of the visual eclipse, and the other line here at the end of the visual eclipse. He actually recorded the first contact here, totality there, and fourth contact there. Well, the odd point, of course, is that these bumps, which are not supposed to be there, actually occur while the moon is overlapping the corona of the sun. So if the gravimeter is actually measuring gravity, what it's saying at this point at the beginning is that there's a fairly large mass in that direction, not much in the middle, and another large mass at the end. And of course, we actually know that the corona does have mass. The only question is how much. Now, this is only one curve, and I don't know how accurate the data is, but it does give the opportunity to possibly calculate as a first order of magnitude what that mass would be. Let me make one more comment about that. There are all kinds of things going on, including the EU type things. The corona is got high solar winds, slow solar winds. The solar, you saw a picture just before me of the magnetic or whatever fields going by the sun, from the sun to the earth. So there's other things involved, but the approach I would take is a simple one. The gravimeter is measuring mass. If it's out there, let's find out what it is, look at the value, and go from there. haven't done the calculations yet. This is the 1954 Alley anomaly, and people say, oh, no, that can't happen either. They throw that out. If you look at this one, this is the pendulum. The pendulum, of course, is standing still, swinging back and forth, standing still. The Earth is rotating counterclockwise. So it actually looks like the pendulum, from our point of view, is moving clockwise, and that's what's happening here. You can see it progressing. Then all of a sudden, whoop, there was a big kick. They're standing there watching the pendulum, and the silly pendulum just goes backwards, changes direction. So, and then it goes on. Now here's an anomaly inside of anomaly. If you would kind of visualize what's going on from a gravity point of view, that really shouldn't happen. But at the end result, which is interesting, is it starts here, kicks, it goes back further, comes back, eventually on track as if the eclipse hadn't even happened. The 1959 anomaly that he did, again, is strange, but it's much more well behaved. At the beginning of the eclipse, there is a kick. It goes back regularly. At the peak, it levels out and goes the other way and returns to the its point, its normal track. These are the two Alley anomaly. Well, no, I'm sorry. This is the title's wrong. I changed the figure, didn't change the title. The top one is the Wang Eclipse. This is the 1959 Alley anomaly. But what's interesting here is that the Wang Eclipse is measured with a gravimeter, which measures vertical gravity, and yet the motion of the pendulum, where it kicks backwards, is a horizontal force, not a vertical force. So this is a horizontal component of gravity caused by the eclipse. So looking at the general forces, this is, say, at the beginning of the eclipse, where the first bump is, and the force is in the direction towards that, the moon and the corona of the sun. But what we're measuring with the gravimeter is the vertical force. In fact, we're really measuring the negative force, and these arrows represent the forces towards the eclipse. So this is what the gravimeter measures. This is the total force, summing up the x component, the y component, and the z component. So the gravimeter isn't even measuring the full amount of force that's happening towards the eclipse. I put this in here because well before the eclipse, the x component in either direction is 0. But as the eclipse starts, this force starts to increase, and at some point that force is large enough to kick the pendulum to the left. And then it continues until it peaks, and then it starts, well, until the force peaks, but then it starts going back, and at the totality it'll be back here, and then as the eclipse goes to the right, the x component will be in this direction, and finally when it's over, it'll come back. So it's these kicks from that I'm interpreting here, if you will, that these bumps from the Wang eclipse are the kick to give the pendulum the movement to go left, go back right, and end up without any change, ultimate change. So this is just a picture of when the bumps occur. I did this from, if you were standing here looking at the sun, and when you visualize an eclipse, you kind of normalize the sun. Even though it's moving, you follow it along, so it tends to become stationary, and the moon tends to go to the left, and this is the first contact, totality, and the fourth contact. And I've drawn the sun as two parts, a visible sun and a corona. Okay, I've already mentioned that the corona of the sun is an object that contains matter. It has a certain amount of matter, And that's really odd, because if you read anything about it, the one thing I read was that it had 4 particles per cubic centimeter. I mean, that's nothing. So why would there be this bump with such little amount of matter there? And I'm using the word matter as opposed to mass. But the corona's temperature or energy is huge. And I would suggest that the possibility that that temperature ends up having an effect on the mass that the gravimeter actually measured. The assigned mass of the sun is always relative to the 1 kilogram standard mass. And okay, the assigned mass of the sun, the way I'm taking it, is equal to the mass of the visible sun plus the mass of the corona. We can't change, I'm not going to change the total mass that we've used over and over again in the past. We need to stick with that total mass, but now we're going to split it and see how much of that mass appears to be in the corona, how much it appears to be in the corona, sun, visible sun. So you actually need a model to do this, and I tend to do this when I can get to the calculation. And here's the model, a general model I tend to use. This is a 5-body problem. There's the corona, the visible sun, the 2 adding up to the total mass of the sun, the moon, the earth, the lead ball down here emulating the gravimeter. And the idea is to adjust the mass of the corona, or the density of the corona, until I can match the 2 bumps. I don't know how accurate that data is, but it's going to be interesting to find out. Okay. You can use Newton's equation, your own equation. I'm going to use my equation. I've presented it here in the past, and it's not an easy equation, so a 5-body problem with a complex equation is going to be a tough go. That just speaks to the accuracy, which I kind of said. The accuracy, we really don't know how accurate that is. I don't know what value he subtracted. The model is a 5-body model, but I mean, that isn't the real world. That's an approximation. My equation is an approximation. It may be a better equation than others, but it's an approximation. And yet we can get an estimate that no one else has done. Now we're going to go into the timing part of it. We're going to compare the visual image with the gravitational image. Again, here's the time. The gravitational image of the eclipse is there. The visual indication of the eclipse is done by these 2 points. Same thing with the anomalies. Got the time. In this case, we're looking at deflection as opposed to actual gravity measurements. But again, you have the measurement, you have the demonstration, if you will, of this pendulum, and you have the points of the start of the eclipse, the maximum, and the end in all 3 curves. All 3 curves are saying the same thing in terms of time. And what I'm really saying, I don't need to go through that, but this doesn't look like a coincidence. I got 3 anomalies, all 3, each one of them you might throw out and ignore, and yet they have this common timing. Let's review a little bit of the history of the speed of gravity. Newton's action at a distance would generally mean that the speed of gravity should be very high. Lesage, actually a lot of people think his should be very high, but in fact there's no speed requirement for that. All that his particle only has to interact with the object And it doesn't matter how far it came or how fast it was going, it just needs to interact. There's no speed requirement there. Einstein's speed, he says it's a postulate or whatever, an assumption that that speed is constant in a vacuum. It may also say that people interpret further that nothing can go faster than the speed of light. There's a paper out, there was a measurement made in September 8th of 2002 by Sergei Kopykin. Hopefully I say that right. And he measured from a distant star the light bending around Jupiter. He claimed to be measuring the gravitational aberration, and I've never had a definition of that, and he doesn't define it. But the end result is in January of 2003, a big announcement came out saying gravity has been measured the first time. It's never been measured before. That was done by Kopykin and others. Oh yeah, and his result, and I don't have any data. I have a report, but I don't have the data. It's more of a media announcement. But he said that gravity was the same as the speed of light, plus or minus 20%, and it was measured for the first time. Karazani is someone that got Dave started in this, and Dave got me started, so I've read him a little bit, and he referenced a man named Bayliss from a university who calculated the speed of gravity at 27 C. But you're all probably more familiar with Van Flandern. He has, in the book Pushing Gravity, he has listed 8 different situations, events, where the speed of gravity has to be very, very fast. And the lower limit of all of those is 2 times 10 to the 10th times the speed of c. And yet some people will say, I've talked to some people, oh yeah, gravity is the speed of c. It's just intuitive to them that that's what it must be. It's just got to be the speed of c. This is Tom's third reason. A non-null body experiment involving solar eclipses in the Sun, Earth, Moon system, showing that optical and gravitational eclipses do not coincide. But he's saying they do not coincide. That's all he says about that in particular that I have. But I would say, well, I don't have that other figure yet. But I would suggest to you that having seen the LA anomalies and the Wang Eclipse, I think they coincide. Excuse me, I think Van Flander's wrong. And one of the reasons I'm going to try to get into a little bit of detail here is because sometimes there's confusion about where the sun is. Your mom and dad probably said when you're growing up, look up there, there's the sun. That's not there, and probably most of you already know that. If you, dang it, I push it when I push it hard too. When you think the visible sun is here, it is actually about 2.083 degrees to right, which means that by the time when the physical sun was here and emitted light, it moves down here after 250 seconds, and then down here where you see it, the physical sun has moved over to here. You think it's up here, but there's nothing there. What you see is down here. It's in your eye and it's in your brain. That sun is not there. The irony is you can't see that either. If it just got there, it's just emitting light. You can't see it. You can't see it. It's over there, and we're standing here. The light has come all the way down there. We see it here in our eye and our brain, and that our brain tells us it's up here. Okay, now let's back up to the point where the physical sun. By the way, let me make a comment. I think it was on the previous slide, but I didn't say it. The previous slide, I had a note that said, the visible sun cannot cause an eclipse. It's only the physical sun, physical moon, that the gravimeter actually measures. So it's the physical sun that we have to track. And then, so I put the physical sun up here and the physical moon there, and this is where we think the visible sun is, but its image has already come down here. So when this physical sun is here, the light gets emitted and it propagates and it comes down, passes by the moon, hits our eye, and by that time this spot has moved over to here, and so we see the sun here when after 500 seconds after it got emitted from that point. Oh, I take it back. I did cover it. The visual sun is down here, and it can't cause an eclipse. So the main question here is, how can the gravitational image appear on the surface of the Earth at the same time the visual image occurs? In order for both images to appear on the surface of the Earth, the gravitational image must be generated at the same time that the light was emitted, and they both reach the Earth at the same time, indicating that the speed of gravity is about the same as the speed of light. I'm going to go back to this one. We just went through the we talked about the light being emitted coming down. Now we see the gravitational image down here using the gravimeter. Well, how did it get there? Well, the only place that image can come from is here and here. So whatever is there is coming from this sun, from the physical sun, to the physical moon, down to here, giving us that gravitational image. Okay. The Wang eclipse doesn't actually give a speed. You can't tell from the Wang eclipse how fast gravity is by itself. It only shows that they're about the same. It's my opinion that that curve, the Wang eclipse curve, can be generated if the speed were 1/2 c. If the speed of light were 1/2 c. If the speed of light were 1/2 c, then for those images to appear at the same time, then the speed of gravity would be 1/2 c. And I contend that same image would be captured by the gravimeter. Or it could be 27 times c, and you still get the same image for light and gravity traveling at the same speed. So the calculation I'm going to make is not 300,000 kilometers per second. I'm going to calculate a ratio. The speed of gravity to the speed of light is going to be equal to a number somewhere around 1, somewhat lower maybe, somewhat higher, because remember, the data may not be that accurate. And it's going to have a variation depending on when I substitute the speed of gravity into the model. I may be able to make it a little faster, a little slower, and still get a reasonable image that was captured by the Wang eclipse. Well, this is looking at it from a different point of view. If the speed of gravity is very, very high, then it would have had to come from this position, and the image, since this can't give you a gravitational image of the eclipse, it has to be this physical sun and this physical moon, and it would appear sooner, or at least over to the east of where the gravimeter was placed. Well, this probably, I don't probably need to talk about that, because I'm sure almost all of you know the sun is not where you see it, and the further you have aberration of light, which moves it to the left by 20 arc seconds as well. That's my presentation. I am saying that this will give you a more accurate measurement of the speed of gravity, more accurate than 20% that Sergei got. And this information was available in 54, 59, and 97. And people just threw it aside. Thank you.
We've got time for some questions. Anybody want to come up? Come on up.
So I guess I'm wondering if the effect here is that the moon is blocking gravity from the corona. As it moves across the corona, the gravitational effect is blocked from the corona.
That's what it would, I guess that's what it would appear, but let me just say this. With this presentation, I didn't propose any theory.
Okay, to me it implies the existence of the ether, because if the moon and the mass of the corona were together in one place, there would be no blockage. But because there is space between the two, there is blockage. Does that not imply the existence of some sort of ether between the corona and the moon?
And I guess I could say yes. I'm not exactly a proponent of ether, but I could also tell you that people who think gravity is a pressure and a high pressure and a low pressure, you can explain it. If you have a theory of gravity, my challenge to you is if you have a theory, you should be able to explain why this is happening. You know, whether it's dipoles, whether it's particles, whether it's electromagnetic waves, you should be able to explain it. Just to throw, oh, I'm sorry, there's a question.
I was just asking if gravity is instantaneous or is not instantaneous, which is what you're suggesting. Is Newton totally wrong in that case about the orbits of the planets? Because surely
You know, that's quite interesting. You see the image of the sun and the image and the gravitational image, really like with the tides. You use the visual image to match up with the tides, even though they're maybe sluggish because they're a fluid, but we match them up that way. And if you saw that one figure, as the force of gravity and the light proceed down to the Earth, the image comes over and it lines up and it looks like Newton's equation works. Newton's equation works because, or I can explain Newton's equation, because like Tycho and Kepler used data on their visual image of where the things were. You take Newton's equation and it works, but this doesn't negate that at all. I think action at a distance comes from, I skipped 2 slides at the end.
I'm sorry, I've got the next one.
No, that's okay, I don't.
You asked if anyone had a theory of gravity. I have one here. It's a paper that was in the back of the room. I don't know who got it or how many, but I'd like to discuss it with you afterwards if you have time. Thank you.
We have one more. We have a question. One more.
What was the percentage of change of the gravitation? Was it 1% or 1/1,000,000 of 1%?
The change?
Yes.
You know, that's a good, you know, I think what you're asking me is the bumps look really big.
Yes.
Oh, that's all right.
Since I haven't done the calculation, I can't tell you, but it might not be that much change in the gravitation.
Are there any units on your chart?
I'm just about.
There's 7 microgals is the peak of those 2 bumps.
Micro what?
Gals. A gal is 10 to the minus 8 centimeters per second, something like that. And a microgal is even less than that. Gal is named after Galileo, but that's how a gravimeter measures it, 7 microgals.
All right, thank you.